Welcome to NPTEL lesson, a basic course to electric and magnetic circuits. In this lecture, we will further on our discussion on transformer. Today's topic is on ideal transformer, and then followed by we will talk on impedance referred to primary, how impedance in the secondary can be transferred to primary. Let us define what is ideal transformer, and then we will go to the more practical transformer. The purpose of introducing ideal transformer here is that we learn different terminology related to transformer principles and operation, and then based on that foundation we will move for more realistic transformer. We have already discussed on transformer as a magnetic circuits. On that perspective, there are few assumptions for an ideal transformer. The first one is that the different windings on the transformers, they have negligible resistance. Then we have no leakage flux. We know what is leakage flux, that the flux which are waste and does not link to the other winding, does not go through the core. So, we assume that the flux confined to the core only and it links to both windings, there is no leakage flux. Third point is permeability of the core is so high that the net MMF required to establish flux in the core becomes negligible. Permeability is very high. So, the mu r relative permeability becomes much higher. Therefore, the exciting current required to establish flux in the core I m becomes negligible. And the fourth point is the core loss is assumed to be negligible, no hysteresis and eddy current loss. This is a hypothesis of the transformer, as already mentioned. To better understanding of the functionality and principle of operation of transformer, we have started with these assumptions which we call as an ideal transformer. So, in this transformer model, we have two winding transformers. Whenever we energize the first one, a small amount of magnetizing current flows here, which establishes a flux in the core, and this flux links to the second coil. So, in the second coil, and induced EMF governed by Lenz's law happens to be there in the form of E 2, and this E 2 is available at the terminal of the secondary coil, secondary winding, and this terminal voltage becomes V 2. And we say that E 1 and V 1 are almost equal, and so also the E 2 and V 2 with this assumption in this case. Before going to the functionality with ideal transformer, we need to know the no load condition and the loaded condition of the transformer. The no load condition, as we see here, this is a two windings in a cell type transformer. So, this is our the first coil is the primary winding, and the second coil is our the secondary winding. The primary winding is energized with a voltage V 1, and it has a magnetizing current, and this magnetizing current results in flux in the core. So, which goes from this path and then divided into 2. This flux links to the second coil, and then we get the induced EMF here. And then to simplify this for understanding purpose, as already mentioned in earlier lecture, we have this two winding and different limbs. Now, what happens here, that as we say here is a no load condition, the corresponding secondary terminals are kept open, no impedance is connected to the secondary. This is called no load condition. As a result, there is no current in the secondary, I 2 becomes equals to 0. So, this is the situation which we call the system to be a no load condition in the transformer. Similarly, a loaded transformer becomes, we connect the secondary with an impedance Z L. So, analogous to that one, this becomes this. So, thereby what happens, the V 2 available here, voltage available at the terminal of the transformer, that results in a current I 2. So, this I 2 becomes equals to V 2 upon Z L, in phasor terms V 2 phasor upon Z L, and that results in a current I 2. So, there will be a change in the primary side perspective current, and that current becomes I 1. So, this is about the loaded condition. Note that depending upon the Z L, 1 ohm, 2 ohm, 1 plus j 1 ohm and so on, the corresponding I 2 happens to be there. So, the I 2 lags or leads depending upon the impedance angle Z L upon with respect to V 2, and the corresponding I 2 value becomes higher when Z L is smaller, and Z L is higher, the corresponding I 2 value becomes Z L is higher, then corresponding I 2 value becomes smaller. So, this is about the two conditions of the transformer, a no load condition and a loaded condition. We will elaborate on this. So, our assumption is that the transformer is an ideal transformer, and first we will talk about the no load condition. So, there is no impedance connected at the terminal of the transformer. As already we have seen for transformer principle. So, at this moment an magnetizing current flows in the primary with the energization of the sinusoidal voltage V 1. Let the corresponding flux in the core becomes a sinusoidal flux phi m sin omega t, and we know that d phi by dt governs the provides the corresponding induced EMF in primary and the secondary with the flux established through the core. So, d phi by dt. So, we got this E 1 to be 2 pi f n 1 phi m sin omega t plus pi by 2, and then similarly E 2 equals to 2 pi f n 2 phi m sin omega t plus pi by 2. So, the difference between E 1 and E 2 is about in terms of number of turns n 1 and n 2 respectively. Both have same frequency f, and both have same flux linking to these two. So, this results in the corresponding ratio E 1 upon E 2 to be n 1 upon n 2, and if you take these two into the phasor terms from these instantaneous values, then the E 1 upon E 2 phasors, that also happens to be A equals to n 1 upon n 2, that is the turns ratio of the transformer, that we have all defined in the earlier lecture. Now, at these situations, if you see this circuit as a magnetic circuit, so we see that there is an ideal transformer. Primary is energized with a sinusoidal voltage, results in a magnetizing current. So, that becomes equals to n 1 into I m, instantaneous value, establishes an instantaneous flux in the core, and then the corresponding S. As already mentioned, in terms for the ideal transformer case, this S becomes negligible, tends to 0. So, therefore, this n I m equals to S into phi, the n I m becomes negligible, and that is the point we say that the I m current to establish flux in the core required is very, very small, with the assumption that the permeability of the magnetic core is very, very high, and that results in H to be tending to 0. From phasor diagram perspective, if you see, if this is the phasor phi, sinusoidal phasor phi, then the corresponding current which establishes the flux phi is I m magnetizing current, very small as compared to the capacity of the transformer current in terms of the current. Corresponding E 1 leads the flux by 90 degree, and so also V 1 is very close to E 1 or V 1 is equals to E 1. So, this V 1 and E 1 lead the flux and or I m by 90 degree. This is what the corresponding phasor diagram at the no load condition of the ideal transformer. Now, we will go to the loaded condition of the transformer. So, now an impedance is connected to the secondary, a current flows in the secondary, I 2 current flows in the secondary. So, in the schematic diagram we can see also like this, there is an ideal transformer and with a turns ratio of N 1 is to N 2, and then a current I 2 flows here and a current I 1 flows in the primary side. Now, if you go to this magnetic equivalent, then we see that at this condition the MMF provided by this primary is N 1 I 1 instantaneous value, and the MMF which will be there across the secondary terminal, that becomes equals to N 2 I 2. But we know that this N 2 I 2, the corresponding current which will be flowing in the secondary is governed by Lenz's law, and this current should be such that it establishes flux in the core to oppose the cause. The cause is nothing but the flux provided by the primary. So, therefore, the I 2 will be rather the ampere turn in the secondary coil N 2 I 2 will be in opposition to the N 1 I 1. That results in, if this will be, we provide the corresponding symbol to be plus and minus, this will be minus and plus. So, they both oppose each other, and then the path between these two coils will be S, the reluctance, but for an ideal transformer the S is tends to 0. So, the ampere turn in the core becomes equals to 0, because ampere turn in the core equals to S into phi. So, this results in the corresponding equivalent magnetic circuit to be like this, and from this we conclude that N 1 I 1 equals to N 2 I 2. The ampere turn, instantaneous ampere turn provided by this primary equals to instantaneous ampere turn that in the secondary. To further our loaded condition discussion for the transformer with I 2 current flowing and the corresponding magnetic circuits, we will see in terms of the phasor value I 1 and I 2. Now, we know that the I 2 current from the earlier discussion on instantaneous values is N 1 I 1 equals to N 2 I 2. So, that results in corresponding N 1 I 1 phasor equals to N 1 I 2 phasor, but I 2 phasor equals to V 2 upon Z L, where Z L is the impedance connected in the secondary. So, that is equals to, again we know that for the ideal case V 2 happens to be equals to E 2. So, we put E 2 upon Z L. So, this is the corresponding current voltage relation at the secondary, but we know that the phi in the core remains constant as E 1 remains to be fixed, because V 1 remains to be constant, V 1 and E 1 are same. So, this results in that the corresponding further things, that the ampere turn in the core plus the ampere turn in the secondary coil, that equals to ampere turn in the primary. So, that we know ampere turn in the primary provided equals to ampere turn in the secondary plus the ampere turn in the core, but the ampere turn in the core tends to 0. So, therefore, ampere turn 1 equals to ampere turn 2 in the for the circuit. This results in N 1 I 1 phasor equals to N 2 I 2 phasor, and therefore, I 1 phasor upon I 2 phasor equals to N 2 by N 1 from this relation, and that equals to 1 by A, the turns ratio of the transformer. But you know the turns ratio of the transformer, from that 1 by A equals to E 2 upon E 1 equals to V 2 upon V 1. So, this from the ampere turn balancing we find a relation like this, that I 1 phasor upon I 2 phasor equals to 1 by A equals to E 2 phasor upon E 1 phasor equals to V 2 phasor upon V 1. So, the turns ratio and the phasor ratio of current and voltages of both sides can be related as shown. From this, if you take only the magnitude of voltage and current of these phasors, then we can also say that V 1 I 1 equals to V 2 I 2 phasor in terms of magnitude. So, that is nothing but the apparent power in the primary to the apparent power in the secondary. Similarly, if we take this corresponding I 1 conjugate upon I 2 conjugate, that also happens to be 1 by A, and then from I 2 conjugate upon I 1 conjugate equals to 1 by A, and this equals to again V 2 dot divided by V 1 dot, the corresponding phasor. So, we multiply this term. So, we say that this is I 1 upon I 2. So, this equals to 1 by A, and this becomes equals to V 2 upon V 1. So, if we multiply this, so this becomes equals to V 1 I 1 conjugate equals to V 2 I 2 conjugate. So, this implies that the complex power in the primary equals to the complex power in the secondary, but complex power is nothing but P plus J Q. So, therefore, we conclude that P 1 plus J Q 1 equals to P 2 plus J Q 2. Complex power in the primary equals to complex power in the secondary. So, that is why we clear here. So, from the loaded condition we conclude that for an ideal transformer I 1 upon I 2 equals to 1 by A, and that equals to V 2 upon V 1, and the complex power which will be there in the secondary, that is P 2 plus J Q 2, will be at that time the corresponding power is P 1 plus J Q 1, where P 1 Q 1 P 1 plus J Q 1 is V 1 I 1 conjugate, and P 2 plus J Q 2 is V 2 I 2 conjugate. Now, let us see an example. So, as the statement, a 440 volt by 110 volt single phase transformer has a load current of 120 ampere 0.8 lagging power factor, and in this case the corresponding transformer find the primary current and the real and reactive power at the primary side. So, as per the statement in this problem, this 440 volt corresponds to your V 1 and 110 volt corresponds to your V 2, and the corresponding current, load current. So, this corresponds to your I 2 phasor equals to 120 ampere, 120, and this is a lagging current. So, this is minus cos inverse 0.8. This is with respect to the reference, if we consider V 2 phasor to be equals to 110 with angle of 0 degree. So, this is then the question asks is that find the primary current I 1 phasor and the real and reactive power at the primary side, that is P 1 and Q 1. So, we go by this, and the corresponding equivalent circuit diagram as we have learned till now is about the transformer here, and then we have this P 2 plus J Q 2 with the I 2 current here and V 2 here, and the corresponding power complex power happens to be balanced. So, S 1 complex power, and here this is S 2. So, we know that S 1 equals to S 2. So, P 1 plus J Q 1 equals to P 2 plus J Q 2. So, that becomes equals to V 1 phasor I 1 conjugate equals to V 2 phasor I 2 conjugate. So, now we know that we have the corresponding transformer turns ratio. So, from the voltage transformer ratio also A equals to 440 upon 110. So, this equals to 4. Now, we have I 2 as already mentioned, I 2 equals to we have 120 with an angle of cos minus of cos inverse 0.8 and the corresponding I 1 we know N 1 I 1 equals to N 2 I 2. So, I 1 phasor equals to N 2 I 2. So, therefore, the corresponding current becomes equals to I 2 upon A and this reaches to 30 with an angle of minus cos inverse 0.8, that is minus 36.87 degree. So, this gives us this corresponding I 1 and from there on we know this corresponding B 1, B 1 is 440 with angle of 0 degree, B 2 we have also considered to be 0 degree. So, that leads to the corresponding B 1 into this I 1 conjugate. So, that is into 30 with an angle of plus angle now cos inverse 0.8. So, this is nothing but your P 1 plus j q 1 and from there real part will give you the P 1 and reactive part will give you the Q 1. Results in the corresponding this to be I 2 to be equals to 120 minus 36.87, primary current is I 2 upon 4. So, that results in 30 with an angle of 36.87 and then V 1 A 1 conjugate. So, we get this to be 440 into 30 with an angle of plus 36.87. This results in P equals to 10560 and then the corresponding complex reactive power part 7920 volt ampere. So, real power happens to be 10.5 kilowatt and the reactive power happens to be 7.92 kVAR. So, from this example we see that how the corresponding voltages of the primary and secondary coils are mentioned. Based on the load current we can find out the corresponding primary current and then how the corresponding complex power matching happens to be there in the primary and secondary side. So, we say that we have V 1 I 1 conjugate equals to V 2 I 2 conjugate. So, this results in equals to P 1 plus j q 1 equals to P 2 plus j q 2. That implies that the question asks it about the P 1 and Q 1, but similarly P 1 will be equals to P 2 and Q 1 will be equals to Q 2 for this ideal transformer case. Now, the second point on the loading condition of the ideal transformer we will discuss on impedance transfer to the other winding. Let us say an impedance ZL is connected to the secondary winding and in this case a current I 2 flows and the corresponding I 1 will flows in the primary balancing the ampere term N 1 I 1 equals to N 2 I 2. Now, this ZL equals to V 2 phasor upon I 1 phasor and A equals to N 1 upon N 2 and that equals to V 1 upon V 2. So, this results in the impedance seen from the primary side. If you see from the impedance seen from the primary side, so that equals to V 1 phasor upon I 1 phasor. So, that becomes equals to A 2 V 2 phasor into I 2 phasor by A, V 1 is A V 2 and I 1 is I 2 upon A. So, that results in the corresponding impedance seen from the primary becomes equals to A square V 2 upon I 2 and that equals to A square ZL, because we know that V 2 by I 2 is ZL. So, this results in the impedance seen from the primary side, source side, supply side, it results in with an impedance ZL connected in the secondary to be equals to A square ZL and this we define as ZL dash here in all the transformer terminology we will discuss will be dash refers to the corresponding value to the other side. ZL is connected to the secondary. So, ZL dash corresponds to the primary side, because we mentioned here the impedance seen from the primary side. So, all the dash term here represent for the other side of the winding. From if it is secondary connected, then it goes to the dash corresponds to the primary. If it is primary connected, if we refer it to the secondary, then the corresponding dash refers to the secondary. So, ZL dash referred to the primary, this happens to be equals to A square Z L. So, for example, if A is equals to 4 and we have a Z L equals to 10 ohm resistance, then the corresponding primary resistance Z L dash becomes equals to A square into Z L. So, this becomes equals to 4 into 4 16 into 10, this becomes 160 ohm. So, this is about how the corresponding load impedance when connected, and then how does it seen by the source side, that is the primary side. So, from this relation we got this to be A square Z L. Now, the equivalent of this one, so from the primary side if we see, then you can say that the equivalent electric circuit diagram becomes Z L dash, which equals to A square Z L, and that equals to the V 1 and the I 1 phasors. So, V 1 upon I 1 phasor equals to A square Z L. So, this is about the equivalence between this circuit, left hand side circuit and the right hand side circuit. So, in overall, this ideal transformer provides us this conversion of that the corresponding secondary impedance, which is connected, the load impedance connected, can be referred to the primary side. We take multiplication of the term A square, that is turns ratio. In a similar way, the secondary quantities voltage and current can be referred to the primary, why V 2 dash which referred to the primary equals to A V 2, because we know V 1 by V 2 equals to A and I 2 by I 1 equals to A. So, therefore, the corresponding I 2 dash becomes equals to I 2 by A and V 1 dash V 2 dash becomes equals to A V 2. V 2 dash here implies the primary side voltage for a voltage of V 2, I 2 dash here refers to the primary side current for a current of I 2 in the secondary. So, in total for an ideal transformer we discuss about 3 things, that how the corresponding load impedance connected in the secondary is referred to the primary, how the secondary voltage is referred to the primary multiplying by A, and how the corresponding current referred to the secondary current referred to the primary divided by A. Now, we will see an example now. The challenge is in a system like this, where we have a power supply and a speaker connected to the power supply. The power supply has a 10 volt open circuit voltage and 1 ohm internal resistance, and this is connected to a speaker. The challenge is how to maximize the power transport to the speaker. Challenge is how to maximize the power transport to the speaker. So, in this case the power transfer is that the corresponding current through this path becomes this AC circuit 10 upon 10, that results in 1 ampere of current, and therefore, across through the 9 ohm resistance I square R will be there. So, the power associated with the speaker becomes 9 watt. Now, the challenge as mentioned to maximize the power transfer to the speaker, so that the performance of the speaker can be enhanced. In this sense, we know that maximum power transfer theorem that says that for this source the maximum power transfer can happen if the corresponding load impedance becomes equals to 1 ohm. For this case, as we have studied in single phase AC circuit, that from the power transfer perspective for the power supply, that if the load impedance happens to be there 1 ohm, then the power transfer to the speaker can be maximized. So, from that we can connect a transformer across the terminals of the speaker as seen here, and this transformer is connected to the speaker. Now, what happens here by this way, as you have studied, that the resistance on the speaker now is connected to the secondary terminal of the transformer here. So, therefore, the resistance which will be seen from the supply side, the primary side will be now A square R 2, R 2 is this side. So, therefore, this R 2 A square R 2, where A is equals to N 1 upon N 2, and this R 2 equals to 9 ohm. But as we say from the power transfer, maximum power transfer, the corresponding R 1 R 2 dash, which will be seen from the primary side should be 1 ohm in this case. So, that results in 1 equals to A square into 9 from this relation. So, this A becomes equals to 1 by 3. It means, the n 1 by n 2 that becomes equals to 1 by 3. So, results in n 2 to be equals to 3 times that of the n 1. So, if we connect like this, then the corresponding primary resistance seen becomes 1 ohm, and that results in a matching of the resistance to have maximum power transfer from the power supply. So, if you see here, so this A equals to 113 ohm, and then the corresponding equivalent diagram becomes now from the primary side, from the supply side here. So, this is supply side. So, from the supply side, this becomes equals to 1 ohm. So, therefore, the corresponding power, corresponding current becomes equals to, at this condition, become 10 upon 2. So, that results in to be equals to 5 ampere, and this results in the corresponding power associated with this 1 ohm seen at R 2 dash equals to 5 square into 1 equals to 25 watt. So, this is about the 25 watt. So, earlier you are getting 9 watt, the speaker was getting 9 watt for this connection, 9 watt, but now in these connections the speaker gets now the power transferred to here becomes 25 watt. So, this is about how to optimize power transfer to the speaker, so that the performance can be enhanced. So, this is an example how a transformer can be useful for this kind of situation. Now, I will go to a similar example, how in a descriptive manner a power amplifier has a no load voltage of 20 volt. A power amplifier has a no load voltage of 24 and an internal resistance of 18 ohm. So, 20 volt and 18 ohm, this is a power amplifier which is the source of the supply. To be used with a 8 ohm speaker, the speaker resistance is 8 ohm. Calculate power delivered to the speaker when it is connected directly with the amplifier. So, the power here becomes equals to I square R, where I equals to V upon I 20 upon 18 plus 8. So, this into R. So, this is about the power. The turns ratio of the transformer to maximize the speaker power. So, like we discussed about earlier. So, now we will connect, you can say that the corresponding transformer across the power supply. So, this power amplifier circuit will connect the transformer. Let the transformer turns ratio is A equals to N 1 by N 2. So, now this side is 8 ohm. So, this is 18 ohm. So, from the primary should see this R 2 dash equals to 18 ohm, but R 2 equals to 8 ohm. So, therefore, R 2 dash equals to A square into 8 it equals to 18. So, this is equals to R 2 dash equals to 18 equals to A square into 8. So, this results in A equals to 1.5, this equals to N 1 by N 2. So, if we connect the corresponding transformer turns ratio of N 1 by N 2 equals to 1:5, then the maximum power to the speaker becomes the current. So, the R 2 dash will be seen as 18. So, that results in the current to be equals to, in the second case, I equals to 20 divided by 36 ampere, and I square into the corresponding 18 will be the power transfer in the second case. So, the power transfer in the second case becomes 5.55 watt as compared to 4.73 watt without the connection of the transformer. This results in the corresponding maximum power delivered to the speaker, and this is a using the matching transformer case. So, this is the application how we can use for the improve speaker performance and so. In general, from this lecture we see the what is an ideal transformer and how does it function in open circuit condition and loaded condition. Then we talk about that in the secondary an impedance is connected as a load impedance, how the corresponding impedance is seen from the primary, we call it a referred to primary. So, in terms of the secondary quantities impedance, current and voltage, we refer to the primary using the turns ratio A. Thank you.